So in this video, we're going to start exploring the regularity property of the trajectories of the Brownian. Now, we know they are almost surely continuous. There is even part of the definition of what a Brownian motion is, but are they better than continuous, right? And if you plot them, they look something like that. They look fairly rugged, and we're going to show that they really are very rough in the sense that they are nowhere differentiable. And that's a serious limitation in the way we can build a calculus, the way we can build stochastic analysis with the Brownian motion as our quintessential example or as our building block for the class of stochastic processes that we'd like to study. So in order to understand exactly, well, in order first of all to prove that the Brownian is nowhere differentiable and understand how far or how close it is from being differentiable, we're going to measure the regularity of the trajectory in terms of Hölder continuity. So let me recall this definition for you. When I have a function, let's say on 0, 1, it's say to be Hölder regular of parameter alpha for some parameter alpha if there exists a C such that for every T and S in 0, 1 f of T minus f of S is smaller than this constant times T minus S to the alpha, right? And that's a definition, let's say, for alpha between 0 and 1, but notice that this is consistent with the notion of being C1 that you've seen before, right? If you're differentiable with a continuous derivative, then you're going to have the fact that for every T and S by the mean value theorem in 0, 1, your f of T, maybe C1 on the closed interval, minus f of S is going to be smaller than C times T minus S, right? Being C1 is stronger than what's called being Lipschitz continuous, which is satisfying such an inequality. So what we're going to do now is we're going to find out how large alpha can be, if such alpha exists at all, for the trajectory of the Brownians. And okay, spoiler alert, here's the answer. The Brownian is Hölder continuous almost surely, but only for parameters alpha that are strictly below 1/2. And it's not true in particular for alpha equal to 1. And that's what we're going to exploit to show the nowhere differentiability. So it's really something that's only half differentiable, if you want, and certainly not differentiable anywhere. Okay, so in order to do that, to start being able to measure just how continuous the Brownian is, we're going to recall also the way we've constructed the Brownian, right? We've constructed the Brownian as a sum of independent n0, 1 variable, and then what we did is that we used this Haar basis in order to construct it. So if I index it in that way, right, I use the parameter j to say where on the interval I'm located, and k to describe the scale at which the lengths of the support of the elements of my Haar basis. What I have here is this n01 variable times the inner product of the h2k plus j element of the Haar basis with the indicator function of 0t. Now, for the sake of discussing continuity, the way I've normalized my Haar basis, which was an L2 normalization that I've used in the definition, is not quite appropriate, right? This is a sum k equals 0 to infinity, sum j equals 0 to 2k minus 1, z 2k plus j. Let me remind you that the z ends are IIDs, with z1 being n01, of course all of them being the same, because they're IID, times the integral from 0 to t of h2k plus j of s ds. And if you remember, this has this interesting property that this number here is going to be 0 for all values of j but 1 for any given t. Now the point is, what is the size of that, right? The size of that, I mean, this is a number which either is 0 or is 2 to the minus k over 2, really, right? Because this is the way I've normalized my hk in order to make sure that they had L2 norm exactly 1 to form an orthonormal basis. Now that would make my proofs of continuity annoying to have this 2 to the minus k over 2 factor in the definition of the Haar basis. I'd much rather have this number here, something that is 0 or 1. So in order to compensate for that, I'm going to multiply and divide by 2 to the minus k over 2. Let's multiply that by 2 to the k over 2. And then I'm going to give this a name. I'm going to call that, by definition, delta 2k plus j. So it's exactly like at t. It's exactly like the integral of the Haar basis between 0 and t, except when it's non-zero, it doesn't have value 2 to the minus k over 2. It has value 2 to the k over 2. Okay, and now that means the Brownian is really of the form. It has been constructed as a series of IID n01 variable scaled by a factor 2 to the minus k over 2 times these functions that are take a value 0 or 1. Okay, and now this particular representation and this particular construction of the Brownian that we've used through the Haar basis, which is an example of what's called a wavelet basis, is going to be extremely helpful in discussing regularity properties of the Brownian, because it's reasonably easy to read off the coefficients of a decomposition of a function into functions like the delta n, how regular it is. And this is nothing to do with the Brownian or with probability even. This really has to do with the decompositions of functions into the Haar basis. So we're going to have a little lemma discussing that, and let me show you the statement right now. So here is the lemma about decomposition of function in the Haar basis, globally speaking, that we're about to prove. So we're going to prove something specific actually. We're going to look at functions that are given as sums, weighted sums of the delta n's, right? So the delta n's are these renormalized integrals of the Haar functions between 0 and t that we've been discussing here. Now, so and Cn will be a sequence of numbers, so these are the weights, and we assume that we're looking at a case where this series converges uniformly, which is the case, for instance, for the random coefficients that we use in the definition of the Brownian. But for now, our coefficients are not random, they're just fixed numbers. Now, what this lemma is telling us, it's telling us if your coefficients, right, for a value of n of the form 2 to the k plus j decay like 2 to the minus alpha times k, okay, then the function you get by taking this linear combination of the delta n is going to be alpha Euler continuous, right? That is reminding you of the definition here. That is to say, f of t minus f of s is going to be controlled by t minus s to the alpha up to a constant, which, I mean, depends on alpha definitely, but just should not depend on t and s. So this is a quantitative form of uniform continuity of the function. Right, so we have a function which is uniformly continuous, this uniform limit of this uniformly continuous function on 0, 1, and we can tell that it's better, it's quantitatively uniformly continuous in exactly this manner as long as we know that the coefficients decay fast enough. Right, so it's really something of the flavor of what you do when you do harmonic analysis or Fourier analysis. So you have series decomposition of the objects you're interested in, and you try to find ways of reading up properties of your functions from properties of the coefficients when you decompose the function into an appropriate basis. Now, the Haar basis we've been using to construct our Brownian motion is particularly good for that. It's particularly good for reading off the coefficients, the regularity properties of the function. Now, let's prove this lemma right now. So linear combinations of delta n's are alpha Euler continuous as soon as the coefficients decay in the appropriate manner. Let's see the proof. So I have a function that's given by f of t equal a sum of a k of something, of the sum j equal 0 to 2k minus 1 of c2k plus j delta 2k plus j of t for all t in 0, 1. And it's interesting to note that really, although I do have a sum of a j here, there's only one non-zero element in that sum because of the property of the Haar basis that makes the delta n, the delta 2k plus j equal to 0 except for a specific value of j that depends on t. So I could define j of t as the unique element between 0 and 2k minus 1 such that delta 2k plus j t of t is not 0. And when it's not 0, it's going to be, what is it going to be? It's going to be 1 or minus 1. Right. So there's only one of them because the Haar basis have integral 0 and are supported exactly on the interval, on one of the intervals of the form, indexed by j. Okay, so that is to say that my f of t, defining that, we have that f of t is the sum of a k of c2k plus j of t delta 2k plus j of t. And well, same for f of s, and I want to look at f of t minus f of s. So really, when I look at f of t minus f of s, I'm going to be summing things of the form c2k plus j of t delta 2k plus j of t minus c2k plus j of s delta 2k plus j of s. So for some t and s in 0, 1. Now what can I say about these objects? I can say that they certainly, just by triangle inequality, smaller than c alpha 2 to the minus alpha k. That's by properties of the ck's. I'm going to get 2 of them, and my delta 2k plus j t of t are both smaller than 1. So that's one estimate, and it's going to be helpful when t and s are not particularly close to each other. It's just going to use the smallness of the coefficients. But when t is very close to s, in particular j of t is equal to j of s, they're in the same tiny interval of size 2 to the minus k, the t and the s, then we can get a better estimate, and we're going to need a better estimate in order to prove the Euler continuity of f of t. So how does that look? If j of t is equal to j of s, then we have that c2k plus jt delta 2k plus jt of t minus c2k plus j, well, I might as well call it j of t. This is the same, delta 2k plus j of t of s, which is what I'm trying to estimate. Let's call that 1. So it's equal to that, and it's smaller than c alpha 2 to the minus alpha k, that's my coefficient, times the increment delta 2k plus j of t minus delta 2k plus j of t of s. And what is that increment? Well, my function delta 2k plus j of t is a function that is either 0 or 1 or minus 1, and if it jumps between 0 to 1 or 1 to minus 1 or minus 1 to 0, it does so in an interval of side length 2 to the minus k, right? I mean, it looks, it's going to, actually not quite, no, it's an integral of that. It's an integral of a function which is like this. So one thing for sure, and this, the size of that interval here is 2 to the minus k. So one thing for sure is that this is a piecewise linear function, the integral of that, and it has to be smaller than 2, I suppose, divided by the length of that interval. So it has to be smaller than 2 to the k. So this is smaller than c alpha, 2 to the minus alpha k, so we pick up a 2 times 2 to the k times t minus s. That's just by the mean value theorem, given that this is given by an integral of a function that is piecewise constant and supported on an interval of size 2 to the minus k. So, yeah, the linearity of the function with this slope gives us this estimate. All right, so this estimate here looks much worse than the estimates we had before, right? Because this decays in k is like 2 to the minus alpha k, whereas if alpha is between 0 and 1, so this actually grows in k. So this looks bad in k, but on the other hand, this is very good if t is extremely close to s, because then t minus s is going to be very small. And the estimate we've got here, by the way, we've just proven it for jt equal j of s, but it works also if j of t is not equal j of s, because if I have that, then I can add and subtract 0 by adding, so I can add this times delta 2 to the k plus j of t of s, because that's now 0, and on the other side I could add c2k plus j of s delta 2k plus j of s at point t, which is 0 minus c2k. Sorry, that's a minus sign. So I don't want this, I want yes, that's right, c2k plus j of t delta 2 of s delta 2k plus j of s. And then you can run the exact same argument as before, except you have two pieces and you use triangle inequality. So you get a 4c alpha 2 to the minus alpha k 2k times t minus s. And now we want to combine these two facts. We want to combine one here, which is an estimate by 2 to the minus alpha k, but without a t minus s, and 2, which is an estimate with 2 to the minus alpha k times 2 to the k, but times t minus s. So how do we do this? Okay, we just say so we take our two t's and s, and we pick L, a natural number, such that, well, the unique natural number, such that t minus s is roughly 2 to the minus L. So it's between 2 to the minus L and 2 to the minus L minus over 2 to the minus L minus 1, right? There's a unique natural number L that such that t minus s is like that, because t minus s is a number between 0 and 1. And now I estimate f of t minus f of s, and what do I get? I get that this is smaller than the sum from k equal 0 to infinity of some differences, and I'm going to split that sum straight away into the part up to L and the part after L. And I'm going to use 1 or 2 depending on which side of L I'm from, on which side of L I'm located. And the idea is, okay, what does that mean that k is smaller than L? So if k is smaller than L, that means that t minus s is very small compared to the scale I'm looking at, right? The scale I'm looking at is larger than the distance between the 2 points. So it's advantageous for me here to use 2, and 2 gives me a 4c alpha 2 minus alpha k 2k times t minus s, which is smaller than 2 to the minus l. And on the other hand, if k is larger than l, then I should not bring this 2 to the minus l. That doesn't help that much. And what I should use, so I use 1 and 2 here, 2 in the first estimate and 1 in the second estimate to get a 2c alpha. Just to be consistent, I might as well estimate the 2 by 4 times 2 to the minus alpha k just by itself. Okay, that was estimate 1 in the second part, estimate 2 in the first part. Now, putting all of these things together, I get what? I get 4c alpha times 2 to the minus l times, okay, I can compute this finite sum of a geometric series, and I'm going to get 2 to the 1 minus alpha l plus 1 minus 1 divided by 2 to the 1 minus alpha minus 1, summing the first geometric series, and summing the second geometric series, I'm going to get a 2 to the minus alpha l plus 1 divided by 1 minus 2 to the minus alpha. All right. And now let's compute all of that. What do we get? We get 4c alpha. And now in the, okay, we get some coefficient here. Let's say the maximum of 1 upon 2, 1 minus alpha minus 1, and 1 upon 1 minus 2 to the minus alpha. I really don't care what that is. It's just part of my constant c at the end of the day. And then I get a what? I get a 2 minus alpha l. The 2l multiplied by 2 to the minus l is 1. And then I get a 2 to the 1 minus alpha. I get a minus something that makes it only smaller. And then the second estimate is just a 2 to the minus alpha l times a 2 to the minus alpha. Okay, and so actually let's put the coefficient, let's put these things here. Sorry, not those. Let's put the 2 to the 1 minus alpha here and the 2 to the minus alpha there. And actually we could, that could simplify any further, but it doesn't really matter. All of that is multiplied by 2 to the minus alpha L. And 2 to the minus alpha L is really 2 to the minus alpha L minus 1, if you want, times 2 to the plus alpha. And that is smaller than 4c alpha times the maximum. Let's bring that 2 in front here. So times the maximum of 1, 2, 1 minus alpha minus 1, and 1 divided by 1 minus 2 to the minus alpha, times this, which is smaller than t to the minus s, t minus s to the power alpha. So this complicated expression here just gives me some constant depending on alpha, and this is the appropriate behavior. Ft minus fs not only goes to 0 as s approaches t, but it goes to 0 as fast as t to the minus t minus s to the power alpha. Okay, so that proves this lemma, which is really just properties of function. So now we remember that our Brownian is a linear combination of delta n, and the coefficients are the following. They are 2 to the minus k over 2, z2k plus j of omega, and then you have your delta 2k plus j of t, j equals 0 to 2k minus 1. So let's recall that. That's for every t in 0, 1, and for every omega in capital omega. All right, and now by applying the lemma, we're going to prove the corollary that if you take any alpha strictly between 0 and 1/2, I mean, you can take it 0, but don't take it 1/2, then there's up to a set of measure 0, so there exists a set in sigma that has probability 1, such that for every omega, or actually such that the trajectory of the Brownian for an omega chosen in that set E are in C alpha. Okay, and what's the proof of that? Well, we only have to show, using the lemma, that there, so I'm fixing an alpha. We only have to show that there exists an E in sigma that has probability 1, and such that for every omega in that E, 2 to the minus k over 2 times z 2k plus j of omega is smaller than some constant times 2 to the minus alpha k. And the constant can depend on omega. So for every omega there exists a c such that this holds 2 to the minus alpha k for that constant c. And then, for that value of omega, we apply the lemma that gives us the continuity of the map t goes to bt of omega for that particular omega. That's why the c can depend on omega. But of course, the c cannot depend on k. So that has to be for all k in n and for all j in 0 to 2 to the k minus 1. That's literally what we need to apply the lemma and deduce the corollary. And you can already guess, right? I mean, this 2 to the minus k over 2 here, the fact that it's a 1/2 in front of the k is exactly why we're going to get this limitation there. All right, so let's prove this. Now, recall that there exists an E in sigma with probability 1 such that for every omega in E, there exists a C such that Z 2k plus j, whatever, Zn of omega is smaller than this constant time, what was it, times the square root of the logarithm of 2k plus j. That was one of the properties of n01 variables using the fast decay of their tails that we've proven along the way of constructing our Brownian motion, or proving that this object that we've defined that way indeed gives you a Brownian motion. So, all right, so you just put these two things together, this property of the IID variables we've used to construct the Brownian, the Gaussians. It's not so much about them being independent, it's about them having fast decaying tails. You put that together with that lemma and basically you get your conclusion. So, because what have we got? Well, if it's smaller than c times square root of log of 2k plus j, then this is smaller than c times square root of, let's say, k plus 1 times log of 2, and that is certainly, well, that's what it is. And so then I have that 2k minus 2 times square root of k plus 1 is smaller than a constant. Okay. Moreover, this divided by 2 to the minus alpha k is going to be uniformly bounded if I take a supremum of a k in n, since alpha is strictly smaller than 1/2. So you see that the strictly smaller than 1/2 is there to compensate for the square root of k plus 1. So there's very limited growth coming from the Gaussians. However, there's still a tiny bit of that growth, and that's why we cannot go all the way to alpha equal 1/2 in that proof. There has to be a little correction. So this supremum is finite. Let's just give it a name. Let's call that m. It's a finite number. And so what do we get? We get that 2 to the minus k over 2 z 2k plus j of omega for every omega in E has to be smaller than this constant c that we had here times the square root of log of 2 times the m that we got there, right? And that's true for every k in n and for every j in 0 up to 2k minus 1. And therefore the lemma applies and we get the Euler continuity almost surely of the trajectory of the Brownian. So up to a set of measure 0, and the set of measure 0 that we had to throw away was exactly the set of probability 0 for on which the Gaussian variables could be growing quickly, but this is only an impossible event. All right, so that gives us a positive result about the smoothness of our trajectories, right? They are almost surely C alpha regular for alpha below 1/2. And what we're going to do next is we're going to show a corresponding negative result that for alpha strictly greater than 1/2, the Brownian cannot possibly be Euler continuous. In fact, that cannot happen at any point of the interval. And in particular, this will show the the fact that almost surely the Brownian is nowhere differentiable as a function of t, which means standard calculus cannot be applied to it